Okay, so in the previous sessions, we talked about sets, and the sets we're particularly interested in this course are you have the set of all possible outcomes of an experiment, which is called the sample space, and then you have subsets of those, so sets of some of the outcomes, possible outcomes. And now that we've discussed that enough, we are going to assign probabilities to those sets. Okay, so we're going to talk about the probability of events, and we'll illustrate these ideas with a few simple examples. Okay. So what we do is we have events, which are sets, and we assign numbers, which are called probabilities, to those sets. Those numbers, those probabilities should be between 0 and 1. And that's the measure of how likely an event is. If you assign a probability of 0 to the event, then that means it cannot happen. And if you assign a probability of 1 to the event, it means that it will most certainly, absolutely, it has to happen. Okay. So 1 means the event is certain. 0 means that the event certainly cannot occur. Okay, so if A is the event that we're considering, then whatever we're talking, whatever outcomes we're talking about, A is a set of possible outcomes of an experiment, then the probability of that event A, of that subset A, always lies between 0 and 1. The probability of the sample space, the set of all possible outcomes of an experiment, is 1. And the probability of no events of this of the possible outcome, the probability of the empty set is set to be 0. Okay, so here's an example. We had an experiment. We flipped a coin. These are thought experiments. They're idealized, so the coin can't land on an edge. Okay, so the coin has to come up either heads or tails, H or T. Then the probability of getting a head or getting a tail, well, head union tail is the sample space. Those are the two possible outcomes. There are no others. So that's the probability of the sample space. And one of the axioms that we're using is the probability of S, the probability of the sample space, is equal to 1. Okay, let's do this with a die, let's say. So we roll a die. You have some sets of possible outcomes. A is that notation means that you could get a 1 or a 2 or roll a 3 or roll a 4. And B says that you could roll a 4, you could roll a 5, or you could roll a 6. These are subsets of the set of all possible outcomes, which are the results of 1 through 6. And so what's the probability of, say, A intersection B? Okay, the probability of A intersection B, well, if we look at A and B, the element which is common to A and B is rolling a 4, and no other element is common. So the probability of A intersection B is the probability of rolling a 4, and that's 1 out of 6, right? If your die is fair, you have a 6-sided die, standard 6-sided die, and it's a fair die, and then the probability of getting any of those results, of the allowed results, is 1 out of 6. So the probability of A intersection B here is 1 out of 6, assuming that the die is fair. Okay, if I don't say fair die, or if I don't say fair coin, assume that this is one in which all of the outcomes are equally likely. Assume that it's fair, unless I say otherwise. Okay, so now with some rules for probabilities, or assigning basically assigning real numbers between 0 and 1 to subsets of the possible outcomes of an experiment. Okay, so some rules. The idea, the events are subsets of the sample space S, which is the set of all possible outcomes. Now, supposing that A is an event and B is an event, what's the probability of A union B? Right, either this event occurring or that event occurring. Assuming that we can work out what the probability of A and what the probability of B are separately, what's the probability of A union B? Now, you can't just sum the two probabilities, right? The probability of A union A is the probability of A, right? It's not the probability of A plus the probability of A, for example. So we need to come up with some rules. If we want to, if we're given two events and we want the probability of their union, or the probability of their intersection, perhaps we want to come up with some rules which will help us to calculate those. Okay, and when you're talking about a union, basically the idea is we don't want to count elements twice. Okay, so here consider this as a Venn diagram. You've got an A that represents the, right. So you have a circle which represents the event A, and it's got some elements in it. And then you've got an event B. So here's a circle which represents the event B, and you've got some elements in B. And you have some elements which are common. So the white region between the two dark regions is the intersection of A and B. Okay, so there's some elements which are counted in both. Now, if we're calculating the probability of A union B, and the elements of A and union B are somehow contributing to the probability, we don't want to be taking their the contributions in the intersection should not be taken twice. Okay. So again, the problem is, supposing we know the probability of A and we know the probability of B and we know the probability of A intersection B, what is the probability of A union B? Okay, and this is the rule. The probability for A union B is the probability of A plus probability of B minus the probability of A intersection B. And the reason you're doing the subtraction is that when you calculated the probability of A, then the elements in A intersection B contributed to that probability. And when you calculated the probability of B, well, A intersection B is a subset of B. So the elements in A intersection B contributed to the probability of B, right? So we've had the contribution from the A intersection B. We've had the contribution of that to the probability twice, and we don't. So we're overcounting, and so now we want to reduce. We want to remove one of those, so that the intersection doesn't count twice. Okay. So the probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B, to avoid double count. Okay, so here's a little test to see if you understand that. Okay, I'd like you to try this on your own. 60% of the students at a certain school, they wear neither a ring nor a necklace. Okay, 20% wear a ring, 30% wear a necklace. Okay. Now, if one of the students is chosen randomly, what is the probability that this student is wearing a ring or a necklace, or B, a ring and a necklace? Okay, so try that on your own and see if you can work it out. Okay, special case for these additivity rules. Let's say we said that events were mutually exclusive or events are disjoint. Sets are mutually exclusive or sets are disjoint if their intersection is empty, if there's nothing in their intersection. Okay, they have no common elements. Then we say that the events A and the events B are mutually exclusive, or they're disjoint. Okay. Now, what's the probability of A intersection B then? It's the probability of the null set, and the probability of the null set, our axiom is the probability of the null set should be equal to 0. Okay. So now, in the special case that A and B are mutually disjoint or mutually exclusive, then the general formula is probability of A union B is probability of A plus probability of B minus probability of A intersection B. Probability of A, probability of B minus the probability A intersection B was the null set. Okay. Well, then the probability of the null set is 0. So that's the probability of A plus the probability of B. So in this special case where A and B are disjoint or mutually exclusive, then the formula reduces to the probability of A union B is the probability of A plus the probability of B. All right, but before you use the simpler formula, make sure that they are in fact at disjoint. Okay, so let's say that we've got things which are pairwise disjoint. So we've got events A1, A2, A3 up to AN. You've got these are subsets, and the intersection of these subsets is the null set when of two different ones, their intersection is empty. Then how do you find the probability of the union of all of these? Well, it's just the sum of the probabilities of each individual event, using the same rule that we've just had. Again, that's a special case when all of these events are disjoint or mutually exclusive. Okay, so let's see how we can use this to work out a simple probability. Okay, supposing that you're going to roll a die and you're going to record the result. Okay, then the probability of rolling, so this event in the curly brackets, this is the event of rolling a 1 or a 2. So the probability of rolling a 1 or a 2 is the probability of rolling a 1 is one event, union with the probability, the union with rolling a 2 is another event. So it's the probability of rolling a 1 or union rolling a 2. Okay, now these are disjoint. If you've rolled a 1, you haven't rolled a 2. And if you've rolled a 2, you haven't rolled a 1. They have, right, there's no, in these two subsets, there's no element which is common to both those subsets. Okay, so then our simplified rule says that this is the probability of rolling a 1 plus the probability of rolling a 2. Okay, well, what's the probability of rolling a 1 fair die? 1 out of 6. Probability of rolling a 2 with a fair die, 1 out of 6. So this probability is 1 out of 6 plus 1 out of 6 is 2 out of 6, or 1 out of 3. Okay, what's the probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6 in a fair die? That should be equal to 1. But if that's equal to 1, but that's also equal to the probability of rolling a 1 plus the probability of rolling a 2 plus the probability of rolling a 3, right? A special case, remember. You can just add the probabilities in the special case of disjoint subsets. And then all of those probabilities are the same because it's fair. So 6 times this probability is equal to 1, the probability of S. So this probability, this equal probability for all the outcomes must be 1 out of 6. Okay. Okay, supposing you have an n-sided die, think about what the extension would be. You have an n-sided die. Okay, once again, I didn't specify, so assume that it's a fair die. You have a fair n-sided die, then the probability of rolling, getting any of the possible outcomes should be equal to 1 over n. Right? We generalize from the previous exercise. Okay, what if we have 3 events? What's the probability of A union B union C? Well, it's probability of A plus the probability of B plus the probability of C. But you overcounted. If you just left it this line here, you've overcounted, right? You overcounted A intersection B twice, and you overcounted. You counted A intersection C twice, and you counted B intersection C twice. So we have to subtract that off. So minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C. But now you actually subtracted off the probability of A intersection B intersection C. Right. So you have to put that back in. All right. So in this case, probability of the union of three events is the probability of A plus the probability of B plus the probability of C minus the probability of A intersection B minus the probability of A intersection C minus the probability of B intersection C plus the probability of A intersection B intersection C. And once again, if these were disjoint events, all these intersections would be the null set, and all these probabilities would be 0. And in the special case of A, B, and C being disjoint, the probability of A union B union C would just be the probability of A plus the probability of B plus the probability of C. Okay. Now let's go to complements. A complement. So A complement is the set of all the elements of S that are not in A. So that means, so this is something that's useful to us. The A union with its complement is the entire set S. Okay. So the probability of A union A complement is the probability of S, which is equal to 1. Okay. Now, by the definition of the complement, A and A complement are disjoint. So that means that the probability of A union A complement is also the probability of A plus the probability of A complement. And then with a little algebra, you will get that the probability of A complement is 1 minus the probability of A, right? Or the probability of A is 1 minus the probability of A complement. Okay. So sometimes it'll be easier to work out the probability of A. So you want the probability of A, but it's actually easier to work out the probability of A complement. So if you want to, in such a case, you would get the probability of A by saying, okay, this is the probability of A complement, and then 1 minus the probability of A complement is the probability of A. Okay, so as I said, sometimes it's easier to work with the complement of a set than with the original set itself. Okay. This is sort of a set subtraction. And I'll read that slash there is set minus. So A set minus B means all the elements of A except any elements that are in the intersection. So A set minus B is A, and then you take away everything in the complement, in the intersection, sorry, A intersection B. Okay. And you can show that then that A is equal to A set minus B union with A intersection B. So A set minus B is A, take away intersection, A intersection B, and then with the union you put A intersection B back, and you're left with A, as you had before. Okay, so that means that the probability of A is equal to the probability of A set minus B plus the probability of A intersection B, which means that the probability of A set minus B is the probability of A minus the probability of A intersection B. Okay, some more rules. The probability of a subset. So A is some event, it's a subset of S, the set of all possible outcomes of the experiment. And if B is a subset of A, then the probability of B is less than or equal to the probability of A. Okay. De Morgan's laws, I'll remind you, we had these last time. A intersection B complement is the same as A complement union B complement. And A union B complement is A complement intersection B complement. Okay. So if you wanted, you might be asked for the probability of A intersection B, but it might be easier to find the probability of A intersection B complement, right? And then that would be found as the probability of A complement union B complement. Okay. Equally likely outcomes. We've already seen a couple of examples of this, right? We're assuming that when we flip a fair coin, the outcomes head and tail are equally likely. Similarly, when we roll a fair six-sided die, all of the outcomes 1 through 6 are equally likely. Okay. So now we're going to apply our rules to the special case when all of the outcomes are equally likely. You should never assume that the outcomes are equally likely, right? They may not be, right? You should have some reason for supposing that outcomes are equally likely. They aren't in all cases. Okay, but let's say that there are. Let's say that there's an experiment, and you can have n, capital N outcomes. So the set of all possible outcomes is S is equal to A1, A2, A3, up to AN, let's say. And individual outcomes are disjointed. Each, you can think of a subset of S which contains only A1, another subset of S which contains only A2, and so on. Okay. So now the probability of S is the probability of this set of outcomes A1, A2 up to AN. Probability of S is equal to 1, of course. And then this set A1, A2, A3 up to AN, that consists of the union of the set containing only A1 plus the subset containing only A2 and so on, plus the subset only containing AN. And now by the rules that we've developed for a probability of unions, and then using mutually disjoint, then we get that 1 is equal to probability of A1 plus probability of A2 up to the probability of AN. Now, if we insist that all of these probabilities are equally likely, then let's call that probability small p. We add all of those p's up, and they add up to n times p. And that means that p is equal to 1 over n. So if you have an experiment, what this says is, if you have an experiment in which all of the outcomes are equally likely, and there are capital N possible outcomes, then the probability of each of those equally likely outcomes is 1 over n. So when we flip the coin, there were 2 outcomes equally likely. So the probability of any outcome, any of those n 2 outcomes, is 1 over 2. When we had a fair six-sided die, each of the 6 possible outcomes is equally likely. So every outcome has a probability 1 over 6. And in general, if you have n equally likely outcomes of an experiment, then that equal probability is equal to 1 over n. Okay. Now let's look at some events. Well, again, we're talking about the case where outcomes are equally likely. Okay, so be careful about that. Don't apply the rules where where the rule is not justified. Okay, so supposing you have an event A, and it consists of n small n elements of the capital N elements of S, and all of those all of the possible outcomes are equally likely. So let's say that capital A consists of the set containing A1 union, the set containing A2 union, and so on, the set containing the outcome A small n. Then the probability of the set A, the event A, is the probability of the set consisting of A1, A2 up to AN. Well, this is the union of the set containing A1 union the set containing A2, and so on up to the union of the set containing AN. And those sets are mutually exclusive, they're disjoint. So then the previous rule says that that's the probability of the set containing A1 plus the probability of the set containing A2 up to the probability of the set containing N. And that's this P, which is 1 over N. So this is equal to small, and there are small n of those, so that's NP. So that's N over N. Okay, so let's do a few examples of these. All right. So I don't know if everyone plays cards, so maybe we should just review that. So a standard deck consists of 52 cards. There are 4 aces, 4 2s, 4 3s, 4 4s, 4 5s, 4 6s, 4 7s, 4 8s, 4 9s, 4 10s, 4 jacks, 4 queens, 4 kings. And those 4